Good morning, Gabriel, the winner of the Good Morning contest, of which there is none. Excellent. Good morning, Vicky, also the winner, not just because everybody's a winner. Good. Oh, and the winner of the, wow, I love it. Okay, I was just seeing that on a video recently. Awesome. Good morning, Jean, also a winner. Good morning, Vanita, also a winner. Good morning, Vincent, who was here very early, so a winner for that. Stop at the winner thing. It's nonsense. Participation awards go to everybody of this generation and all future. Okay. Whoa, did I just kick out Vicky? I'm sorry. Hello. No. Wait, yes. Is it? I think I just kicked out Vicky by accident. Um, oh no, she's here. Okay. Sorry about that. Okay. Good morning. Good morning. Vicky gets the avatar and Jocelyn get avatar awards. Vincent gets animated avatar awards, as does Gabrielle. I have to actually make a portal for that, and I'm going to stop with the awards because it's preposterous. Good morning, Amelia. Good morning. Actually, does Amelia qualify for good morning? I mean, she didn't say good morning. All right, I'm going to stop. Good morning, everybody. Okay, or good afternoon. Good morning, Jocelyn. Thank you. And it is morning. Okay, okay. Welcome back from holidays or observances or celebrations or vacations, etc. We're going to get rolling with some physics equations today and some strange inflections of voice to indicate nothing in particular. So we're going to get to equations fast. And I think we're all you guys. So there's, Big Old Duck is still like due this Wednesday. In other words, homework 6. Some of you have handed in. That's great. People are handing in revisions and getting lots of points. Great, great, great. I feel like the system is like working or you're working it. Um, um, as I think you know, because so many of you responded very helpfully to the announcement, we won't be meeting synchronously this Wednesday. For medical reasons, I apologize. But we'll be meeting asynchronously in the sense that you will watch the video that would be that class material, et cetera, et cetera. And if that's not clear, text me, but it seems like it's clear to most of you. So we're not meeting this Wednesday at all synchronously. The next Wednesday we will meet, but with Professor Lou, et cetera, et cetera. Again, if there's any issues about that, let me know. Okay. So now is that more people are coming in. Where we are now is here. What I want to do, so we're in the middle. Well, we have in principle, we have one last problem to go over, or at least it's actually summarized from homework 5, midpoint velocity. And we just want to start cooking through homework 6, even though again, technically it's not even due till Wednesday, but we're catching up with ourselves. Um, um, but the main thing, so what I want to do today, even if I won't get to that many problems going over. I want to do equations today. I want to concisely summarize material that I believe, well, no, I know for a fact was in the videos that you've been asked to watch recently. Um, um, so so in So in principle, from the videos that you've watched, you would be familiar with the top equation on this board. Oh, thank you very much. Hold on a second. Oh, yes, thank you both. Okay, I'll actually respond to the direct chat. So sweet. In one, thank you. I will. I'll just finish this thought before it runs away. The equations that are on the board right here is the goal of today. They're not, we've never discussed explicitly as a group any of these 3 equations. However, I believe if you've been watching the videos and keeping up with the homework, you will have seen where certainly the top 2 come from, and possibly the third, but certainly the top 2. I'm nonetheless so on the one, I will summarize, like just so you can hear it live or whatever, what's going on with those top 2 equations, because they become very important for the rest of our physics lives, very important. The third one is a little more specific, but anyway, today the point is for me to show you where these equations come from, how to use them. So if you've watched the videos, then hopefully today's going to land the plane for you, cement what's already churning and you're already beginning to practice. And I hope it won't be too redundant. Okay. And if you haven't watched the videos, I mean, if I believed in shame, I would say shame on you, but I won't. Good thing I didn't. But then then from here on in, it's about applying these equations to the various problems in, for example, big old duck. The big goal of all of this, of like everything we're doing right now, the goal is to actually solve the literal problem that is literally called big old duck in the sheet that is entitled big old duck. Like that is the crescendo problem of all of this. And it transitions us to the next unit, which is 2D kinematics. Um, um, you'll know once you can really solve that problem or any, a version of it on your own, you're in good shape for the first exam, which we're not talking about yet, but which will eventually happen. Usually there's a problem on the midterm exam that looks, well, that the physics of which is very similar to the problem entitled Big Old Duck. It often doesn't, you have to know the physics to know that it's the same problem. It often doesn't look, it's not about a duck usually on the exam, and blah, 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 blah. But Big Old Duck is like where we're all trying to get ourselves in a position where we can solve the problem entitled Big Old Duck. Now, again, for anybody who just joined, that's not going to happen today, but that's where this whole ship is heading, to be facile enough with these equations to be able to solve that big old duck problem. Because again, it transitions us to the next unit, which is 2D kinematics. Last point on that, that's also what's going on in lab 4 and 5. Tell me briefly. Well, anyway, lab 4 is very similar to big old duck, whether you see that immediately or not, but they interface with each other intellectually. So by the time we get to lab, and you may do lab 4 before we talk about big old duck, that often happens, but in the back of your mind, understand that lab 4 and big old duck are both about getting us from one-dimensional analysis to two-dimensional analysis. So that's where the ship is heading. Today is all about equations. Even if I don't even really solve one problem, it's about showing you all the equations we have thus far, including these 3 that are on the board that were covered in the videos. And I'll say, and then I'm going to pause for a second, look at the chat and turn the page. But let me say, everything we're doing right now, just to remind you, is technically called one-dimensional kinematics. It's the principles and definitions for motion in one dimension of space. All of these equations, any equation we've gotten so far is it meant to be applied to one dimension of space? And then more specifically, all these equations, as we're going to discuss today, and as the white print on the board right here says, IFF A equals A naught, then what does that mean in English? It means that certainly these 3 equations all assume constant acceleration, which I'm going to discuss in a second. So if you're ever looking up any of this material, like in a textbook, which is not required, or Khan Academy, or if you're just, or in the MSRC, in the tutoring center, if you're trying to get other perspectives on this material, what the material is one-dimensional kinematics. And these equations that we're dealing with now are classically or customarily known as the constant acceleration equations. Okay, that's like our top, and so that's our topic right now, just to be clear. And we're gonna try to land the plane on these 3 equations today explicitly, but in a somewhat summarized way, since I believe you've watched the videos. Okay, now quickly, let me just turn to the direct chat. Very sweet questions in the direct chat about yes, I'm feeling great. Thank you. As you can, I really am. Like, it is true. I guess I do have surgery tomorrow, but it's not because I feel bad. It's too, and I'm not trying to be all personal, but it's straightforward surgery. It's just just for those people who are like learning about medicine at home through this, it's just so they can install a mainline port in me. Like, they're gonna put a port in me so that from here on in, every single chemotherapy treatment, they don't have to like hook up. I don't even know the terms, but so that I no longer have to get fresh needles going in. And I don't mean to gross anybody else out either. I'm sorry, you can leave if you don't want to. The point is that every time you get chemo, it's like through your veins. So you get like a hookup, which means like a needle, and it goes in the same vein. So first of all, that's like sort of painful, and then it sits there for like hours and hours and hours. So, but more to the point, eventually, if you keep doing that, especially on the same vein, which I guess is what they try to do, then eventually you really do damage. One does damage to the veins. So there's a new technology or like modern medicine, they like hook something in you. So then from then, or they install something in you, in me. So that from then on, like there's no more like new fresh needle going in. Like the thing, I don't even understand how it works. I don't know anything about science. I mean medical science. Um, but anyway, that's what's happening tomorrow. But there's recovery or tomorrow, late night tomorrow. So then Wednesday, I won't, blah, blah, blah. I feel fine. Thank you very much. But that's what's happening. And it affects Wednesday for reasons that because of post-op like stuff. Okay. Okay. Thank you. Thank you. Thank you. No, I totally appreciate it. I really do. Okay. So now in terms of equations or in terms of physics, the equations on the board again are the goal. You know them in principle from the videos, but I'm going to like back up and slightly explain them now. In order to do that, I'll turn the page. Boom. This is what we have so far. Let me just change the view on the screen. And I would highly suggest you copy this down, even if you think you know every one of these equations. And I hope you do. Copy this down as like, a growing equation sheet, if you like. Like, make sure you know these things. This is what we have so far. There's like 5 equations going in to the situation before you started watching videos and seeing the other ones that were on the first board, right? This now, and I want to change the view on the screen. Couple of things to say about, and you can raise your hand or put in the chat if any of these is confused. I'm going to briefly summarize all of these now, but very briefly. I'm going to, but you can, especially when the summary is over, if you have issues, let me know. But first of all, notice at the top, I'm saying these are our GDPs so far. I want to pause on that for a second because your homework's been awesome and been coming in, and I've been obviously looking at it. And now my tendency is to put like general comments in the comment section instead of like inline comments. I just think it's like more efficient for both of us. But one theme I'm seeing in the homeworks is there's like there's like a little something confusion maybe or tentativeness with regard to step 3 of the 5-step problem solving method. And step 3 may well be kind of the new step for many of you. Like you always have done some kind of showing of your work for sure. But my view is that what people are used to is showing their work without realizing it, starting at what we would call step 4. I believe things really need to happen before, and that's why people get stuck when they get stuck. Because they either see it right away and then they do stuff and then they don't know why they're bothering to show work because it seems so obvious. Or they don't see what to do right away and they don't see what to do right away. So they don't see what to do. So then they're like, I have no idea what to do. But which I sympathize with, and that was often me. But the reality is the reason when you don't see what to do, the reason is because you're looking for step 4 stuff. You're like looking to do math. Or I was always like looking quickly to do like some algebraic manipulation or something. And if I couldn't see what the algebra was or what equation I should use, then I was stuck. But my argument is that there's really 3 things the brain has to do before you even get to step 4. And one of those 3 things is step 3, which is huge and is different from write down what you know. Write down what you know, which we all learned in 7th grade, really is step 1. Write down what you know about the problem that's in front of you. My point is that also, though, you have to write down what you know about the universe, especially if you're doing physics. You have to write down what you knew before the problem even started, and you got to pick something that's like so self-evident and obvious you don't even think of it as knowledge often, but it often is the piece of knowledge that will lead you to the problem. This is the insight of doing physics, or a insight. So I'm noticing that a lot of people are doing sort of funky things with step 3 GDP, but they don't really know what they're allowed to write down, or they write down weird things. A GDP for step 3. Oh, I'm sorry. Yeah. Melanie, please. Yes.
So is GDP not, well, is step 3 not us writing down the formula that we will be using to solve in step 4?
Okay, that is a perfect question, and you're a perfect person to ask it. I totally appreciate it, and you should totally submit for points. And thank you for slowing me down too. Perfect question. So here's the deal. The short answer is yes and no. The short answer is yes, it is. You're correct. Melanie is correct that step 3 is writing down a thing that you're going to use for step 4. That is very good. And I know for a fact, like I'm thinking of your homeworks. Like I know that that's what you've been endeavoring to do. but here's now one modification for everybody, and it's totally not just Melanie. I wouldn't use the word. I know in the past in other classes, many of you use the word formula. There's nothing bad about that word, especially in a lot of other classes, or say, especially in chemistry. But I'm using a different word on purpose. I would say in physics, we don't want to think in terms of formulas. We want to think in terms of equations, and I'll tell you the difference. And of course, many formulas are equations. Don't get me wrong. This is a subtle thing. But I want to suggest that from here on in, we use the word equation, not formula. And specifically, when we're thinking of equations, the first thing that we want to think of for step three, the first thing we want to look for is equations, when possible, that are like always true. Often these equations have triple equal signs in them. We want equations that make so much sense to us, like to you, like to Melanie, to students. We want, whenever possible in step three, to write down something that by this point, having thought about it, makes so much sense that we actually get it, and we actually find ourselves accidentally memorizing it or accidentally remembering it rather than trying to memorize it. I mean, this is a long road. It doesn't come naturally right away. Um, we want things that make so much sense that once we get them, we like, even if we forget a detail, like anytime anybody says, we're like, oh, yeah, 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 yeah. By which I mean, we really want things that are like true by like definition, not even true by discovery. So here's what I really mean. And the problem with the word formula, of course, we are treating these kind of like formulas in this class. Like, I get the thing about formulas, but here's my issue where I think many people get stuck in their habits with formulas. Formulas often mean little recipes that we come to memorize because we're told to, because someone else has discovered that they work. Like, for example, PV equals nRT from chemistry. Like, I love it. I'm not making fun of it. It's totally true. It's a great law. Like, some of my best friends, like, whatever, love that law. But it's a formula to most of us, even me, because I don't, when I hear PV equals nRT, like, the only reason I know that is because I've learned it and I memorize it, but it doesn't like immediately make sense to me. When I picture it, I'm not like, oh yeah, of course. Like, I don't feel like I always kind of knew that, and then someone was putting letters to it. I feel like I never knew that. And if I know it now, it's because someone has discovered in a lab that it works. And frankly, as you may have learned in chemistry, it only really works under certain conditions. It's like not a law. It's not like a whatever. I'm not. So where I'm going with this is, yes, you are correct. In step three, what we want to write down is things that we're going to use in step four, but we want to try to make them really fundamental. And the things that are really fundamental, if like we in the background, instead of trying to memorize things or practice too much, we want to really think quietly in our mind, like, okay, yeah, everyone keeps saying this is fundamental, but why the heck? Like, I don't think it's fundamental. It doesn't seem like, especially like equation C and E right here on the board. I believe that you don't believe that's fundamental, or some of you are still looking at that like it's gobbledygook. But what I'm suggesting to you is, if I call them a GDP, don't just memorize it. Don't say to yourself, this is some freaking calculus thing that I was supposed to know and I always hated. Like, take it seriously and go back and try to understand, or with me or with somebody else, like, there's an idea behind C and E that once you get the idea, it makes sense. It's not a memorizer, it's a making sense kind of thing. Takes a while, but it does once you, and notice they're all definitions. We're really saying this is the meaning of instantaneous velocity from here on in, or that blah, blah, blah. Now, I'm talking a way lot, but it's really, Melanie's question is really good. And it's kind of like why, like, I'm talking about this, because I want to encourage you guys from now on, if you're looking for a GDP, look for something. I won't always do this, but look for something on the list that I'm giving you here, plus the other three that we're about to talk to today. If it's on that list, it counts as a GDP. But to be really, okay, just to land this plane, the real thing I'm getting at, and again, there are a lot of people that did what I'm about. I'm just gonna wait. Let me just write on a new page and I'll erase it. Like example, to be really concrete, because I saw this in a lot of homeworks. And what differentiates Melanie from everybody else is just that she's like actually having the guts to ask about it. I mean, a lot of people did the following. Um, Um, okay, quick example. Sorry to take so, but again, super important. And then I will move on. Here, you see this equation like at the top of the page. It is an equation and it is true. I'm not like it is true and it's like knowledge, it's information and it's useful. Okay. But I saw this on a lot of homeworks as a way of starting. Like, oh, I mean, as a step three for various problems. Now I'm not mad. I'm actually glad it's why we're doing work together. Like it makes it clear to me where the thinking is. And I'm not trying to shame it. And this might have been totally acceptable. Like you might have seen this in a high school physics class or something, and it might have been acceptable to write down there. And I'm not saying it's not acceptable to write down. What I'm saying is you're thinking it's not a step three because that's not some kind of fundamental idea. That's like if it looks like the fact that the V is on the left side makes it look like it's some kind of definition, meaning, or concept of what instantaneous velocity is, and that's not what instantaneous velocity means. Instantaneous velocity is average velocity shrunken to a limit. What this is a true idea that comes if you take the definition of acceleration, the true GDP that you would want to start with would be this, what I just wrote here in white. Notice it's a definition. It's what average acceleration means. And it signals you, do I think that's obvious? Like you were born? No, I'm not saying it's obvious, but I'm saying that's the thing you want to think about in your private, when you're doing homework or at home or talking to friends. Like you want to think, do I really get that equation? That's the equation I want to understand, not accept on faith, but understand. And you'll know you understand it once your brain goes, oh, duh, that's all that's saying. Like once you think it's stupid, it probably means you understand it because it is stupid. It's not stupid, but it's a statement. Oh, okay, I'm going to get Melanie 1 second. Sorry, I'm talking way too much. But okay, so what I'm saying is the GDP would be that thing in white. Then in step 4, you rearrange it to the thing in yellow. And the reason that I'm insistent on that, there's 1,000 reasons, but one is the problem is if you consider the thing in yellow, if anybody does, considers a GDP, then if you think about it, there's a million ways, not a million, but there's many ways I can rearrange the white statement. And if you think of each of those rearrangements as its own equation, then physics starts looking like this enormous list of equations that everybody thinks they have to memorize or tries to memorize. And that defeats the purpose of physics. Like that may be what it felt like in some other class, but it doesn't work. Ultimately, there's too many equations then to memorize. And if you spend all your brain energy trying to memorize all of them, you never know which one to use when or how to start a problem, which is what physics is really about. So I'm trying to show you guys like where to start, and then so I'm being very technical, but that's okay, Melanie, go. Sorry.
Okay, I'm still confused because um you said that the equation you wrote in white is what you want in step 3 of GDP, right? Okay.
Correct. Yes.
So let's say that we have to use the equation in yellow to solve for step 4. But you said that we can't just write that equation alone. So I'm confused on I don't know what to do. Like
I'm sorry. No, great question. So I'm saying you start in step 3 with the white thing. Then in step 4, you do algebra on the white thing. You multiply both sides by t. And I could do it out if you want, but you
no,
multiply.
that part I get, but let's just say that the yellow equation is what the question is asking us to solve for, right?
Yeah.
Wouldn't that be the only equation in step 3? And then step
No,
4, go ahead
no,
and
no,
solve.
no. Wait. Okay, so I'm glad we're discussing this, but no, that's what I'm saying is like step 3 is a result. It's not a place to begin. Like, yeah, you ultimately need it. I'm not disagreeing with you. Ultimately, you got to get the V on the left-hand side in order to look for V. That's for sure. Yes, that's true. But I don't think you can start with that because like how am I? That would be like if in the question, to take it to the extreme, let's say the question tells you that T is 2 and V naught is 0, and A is 5 or something, and so you're plugging for V. You can't start with those numbers. Those numbers are only happen to be true in the question. The idea that you're starting with is what acceleration means. And from that, you're rearranging it to get what an instantaneous velocity, how to solve for instantaneous velocity. And then you're plugging in numbers. Like maybe it sounds like, it may sound to you like I'm really being like obnoxious or technical, and I'm not trying to be, but I'm just saying that V is not a starting place because that is not in itself an idea. If you start with V, it looks like you're saying this is the meaning of instantaneous velocity, except it isn't the meaning of instantaneous velocity. It's just a way to get instantaneous velocity if you believe in the meaning of average acceleration. I'm saying we always have to start with something like really fundamental and then rearrange it until we get. Let me put it one last way, like, because again, to everybody, this question that Melanie is following up with is not off the topic. Do not think that we are digressing away from the circle of this class, or I mean, tangenting away. This is the class. I'm serious. Like, and everybody should feel free to do more. Like, obviously, we got to cut it at some point, but everybody should feel free to do what Melanie's doing right now and press on these kind of points, especially because honestly, whether I'm talking to Melanie and or everyone, this thing that Melanie is pressing on literally is the issue of physics. It's like what separates being okay at physics to a point versus being able to do physics on our own, like excellently. And it's the difference between physics and math. Like the truth is, Melanie's just articulating what is an issue for lots of people all the time. And it takes a while. And it maybe what I'm saying may be angering people or like annoying you because it feels like if you feel like you already get it and you don't need me to be tweaking the way you get it, I apologize. But I'm saying you're getting it to a point and it will not serve you later on unless you hear this or try this and practice this. So I'm going to put it one last quick way and then I'm going to let Melanie have the last word, whatever she wants to say. And then I'm going to move on, like if that makes sense, just because I don't want to have the last word. But here's my thing, and then Melanie will go, and then if anybody else wants to chime in, please do. I promise you, this is a worthwhile discussion. And anyway, my last way of putting this is, I think, is that what it took me years and years and years of physics to realize that something that I do, and I think I'm not alone in this, something that I do when a problem is a little bit stressful or I'm a little bit stressed, something that I do is I try to write down, or something that I've done in the past, like on an exam or in a homework that's hard. I try to write something down that seems relevant, like V equal, like the question says, what's V? So my brain races to look for an equation for V, and then I write down an equation for V, like Melanie's suggesting. It's like totally reasonable. It's totally common. The question asked for V, so my brain races to look for an equation that stands for V, that solves for V. And then I write it down and like I try to plug in and stuff and get an answer. And when that works, that's great. Like, of course, if it works, it looks great. And it looks like, why is Yaverbaum complaining? But here's the catch behind that is that there isn't always an equation for the thing that you're looking for. The thing that there's often an equation or a definition or a principle that contains the information you're looking for, but doesn't actually directly solve for it. So what I'm really kind of arguing is in this case, it's sort of dumb luck, or not dumb luck, it's like good luck that somehow Melanie and many, many other people have either from high school or from the internet this equation for V, so it seemed like useful to use and they wrote it down and that it seemed to work. But what I'm saying is, hang on a second, actually, that's never an equation that we ever presented in class. So I'm not saying anybody cheated or anything, but I'm saying, wait, it's just lucky that someone already rearranged our equation and put it on the web that way, or your high school teacher did, blah, 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 blah. I'm saying a lot of times, if you just always assume that there's an equation that literally explicitly solves for the thing you're looking for, there won't be. And that's why people get stuck and stop and say, I don't know what to do. I don't know what equation to use, because they're too used to looking for equations that directly solve the problem for them. I'm saying instead of trying to write down something relevant and then trying to make it true, the real secret to physics is first just write down something true. Just write down something fundamental and true, even if you don't meet that's vaguely on the topic, even if you don't yet directly see how to use it, like perhaps Melanie or others don't directly see why the white thing that I wrote is like a good thing. But I'm saying the white thing contains V. So then I'm going to rearrange it in step 4 to make the yellow thing. And I will land this plane right now. The real example of what I'm saying, you'll really understand is if that, even though many of you seem to have this yellow equation that we never said in class, the truth is, what if my question had asked for time? If my question had asked for time, I don't think you'd see an equation on the internet for time in a situation like, and I'd given you all the other information. Then a lot of people would be stuck because there is no equation. There just literally isn't one for time, given all the other things. But if you know the white thing, then you can rearrange it for t. Basically, I'm saying you want to get in the habit of regarding the most powerful fundamental, the most fundamental equations are the powerful ones that can go in all kinds of directions. But the directions themselves should not be memorized or started with. That's like, and again, look, this may all be either boring or annoying to many of you. I'm gonna, just trust me that there's something to even try here. Be willing to try for later on, and you'll see over time. And then over time, if you still reject it, you still reject it. But Melanie, have the last word, and then I'm going to move on.
I understand what you're saying, but I just want to make clear that let's just say that the question is asking us to solve for V in the yellow equation. I would be personally, I would write that equation as my only step three. I wouldn't rearrange it because it's not asking me to find instantaneous acceleration. Am I correct or no?
Well,
So like
you, sorry, I kind of want you to have. All right, I'll answer. Okay, so what I'm honestly saying is you're understandable. Like I totally get where you're coming from. I totally get it. But I'm asking you from here on in not to do that, or to at
so,
least try to
so
try.
so you want us to rearrange the equation just to rearrange the equation? Because it's like I understand, like, okay, I get what you're saying. This is the yellow equation here is the original equation. But then
No, no,
if
no. Wait. No, no, it's not. No, it's not. It's not an original equation. That's what I'm saying. The yellow thing is not an original equation. That's the confusion here. You think it is because it's on the internet or something, but it's not. It's not the original equation. The original equation is the white one.
okay. Okay, I see what you're saying now.
Okay. So, okay. Well, thank you. No, thank you for playing. Seriously, but and everybody, and Melanie should submit for a ton of points. Like any portal that apply. I'm really serious. This is what class is about. This is the virtue of synchronized class. Is that, and if you think it was just one person talking, like then you're not listening hard enough to see how it applies to you. Like, and also, if it was one person today, it'll be you, whoever you are next time. Honestly, this is what class is for. Everybody. Like um, so I appreciate how what's the word, wisely Melanie like handled the whole interaction because it does take a lot of guts to handle that kind of interaction. All right, but cool. So I'm gonna go on. Um, I'm gonna go on. Where am I going? I'm going to, and if anybody else wants to put anything in the direct chat or anything, please do. Okay, so back to these. Okay, so I'm saying these are GDPs. Now I'm also admitting, having said everything that Melanie and I just said, I'll also admit right now, equations C and E, they're calculus, they're intimidating. People have different feelings about them. And why they are GDPs is because they say, like in English, once you understand, they say, in fact, I'll even add, you could write it this way too if you want, what they really are saying is that velocity, instantaneous velocity, sorry, is the first derivative of position with respect to time. Again, you want to get used, that's important. You want to get used to that. You want to go back and refresh what a derivative means, blah, 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 blah. And acceleration, instantaneous acceleration is the second derivative of position with respect to time. Super important, super fundamental, but hard to use directly in step four. Like you often, that's something we would write in step three often, but it's not something you can really like plug into or like do stuff with. You then have to do other things in step four to make it useful, but it's, so they're subtle. But and also same thing with step A. I mean, equation A just says GPR, Galileo's principle of relativity. That's a principle. It's underlying all of this stuff, and there's three forms of it we have so far. The video you're going to watch on Wednesday will introduce you to yet the fourth form, which itself has three cases. So buckle up. But like and I'm not saying any of the, I'm not assuming all of this is fully sunk in with anybody. I'm just signaling to you what we want to eventually get to sink in. So Galileo's principle of relativity, which is so far English, in Wednesday becomes mathematical looking and more directly applicable. But It's English, but it's a principle. And one exam, and it counts as something to write down in step three. It often might be something you're writing down so that you can then choose a coordinate system, make certain choices about your coordinate system or what's going in what direction at what speed. In step four, you'll see that more soon. But anyway, these things, so there's these things, our GDP so far, by far the most useful ones, the ones we've directly kicked into step four so far, are certainly B and D, without a doubt. Okay, that's what we had so far. Then, okay, so I'm moving on now. Then we got into homework four, I believe it was, entitled Average Acceleration, right? And we went over a bunch of problems and used these equations one way or another in a bunch of problems. And then what happened was there was the very last problem. There was the very last problem of homework four, which yeah, maybe I don't want to get myself rabbit hole, but the very last problem, sorry, of problem four, I mean, of homework four, oh, I don't even have it up. The very last problem was a bunch of numbers. Where you were asked to take averages. Right? I want to say this quick again. This was in the video. If I go too fast for you right now, one thing is you should rewatch the video that was assigned on this. But there was a list of numbers in the very last problem. Um, and it asked you to average up each of those lists of numbers. And it assumed that the way that you would average up the numbers, it assumed that you would do the traditional, I mean, you didn't have to, but the expectation was that you would do the traditional thing of like adding up all the numbers and dividing by the number of numbers. And that always works for things like that. And it's called taking an arithmetic mean, right? When you add up all the numbers and you add them together and you divide by the number of numbers, um, you get the arithmetic, meaning add, the mean average, right? And that's totally cool. But what you were expected to discover is that in some of those lists, you could shortcut the whole thing. You could either notice that you could put the numbers in ascending or descending order in some of those lists, and you could just take the middle number. Or if there was an even number of numbers, you could just select like what was in the middle between the two middle numbers, and it would be the same as just adding them all up and dividing. And stop me if that doesn't make sense. Furthermore, you might not have noticed, but if you go back and check, it's true. Once you notice that for certain lists, well, let me pause right there. For certain lists, you could just select the median, the middle number, and it was equivalent to the mean. Right now, it was not true of all the lists. That's why this is a meaningful observation. Like it's not, the definition of median is not the same as the definition of mean. They signify two different things. So that's like triple equal sign, they ain't the same. But double equal sign, they turn out to be the same under a certain condition. For some of those lists, they worked out to be the same, the median and the mean. Oh, okay. Okay. I'm saying when the list of numbers like increased or decreased by a steady interval, by a constant amount, if the list was like 2, 4, 6, 8, or 1, 3, 5, 6, or 11, 7, 3, whatever, if the numbers changed by an unchanging step, then, and only then, the mean and the median were the same. Okay, that's the conclusion from those lists. And by the way, whenever I write IFF, it means if and only if, right? And watch my equal signs. I'm saying mean does not triple equal sign median, but mean does double equal sign median under this important condition. Now, what? Oh, good thing in the chat. Let me see something. Yeah, boom. Yeah, yes. In fact, I'm gonna okay. Yes, awesome. She gets it. Awesome. Now I'm gonna modify that slightly, or like yes. So what Annie's saying in the chat is so the mean only equates to the median. First of all, I like the only, yes. The mean only equates to the median if the variable we are looking for, now we're gonna be careful here, velocity or acceleration, okay, she's covering a lot of ground there, can be plotted as a straight line. Okay, so it's like I love it, and she's bringing us back to physics, which is good because apparently I need to be brought back to physics. So now if we're going to go back to right, because right now I'm just talking like random numbers, but she's saying, oh, I guess this applies to physics, huh? Yes, it does. Let's go to but now if we're going to apply it to physics, let's be super specific. The actual variable, like I'm saying, this list of numbers. Imagine that each one of these numbers specifically is a velocity. Specifically, right? What I'm saying is if you have a list of velocities and the assumption, so if the dependent variable is literally instantaneous velocity, and if the independent variable is time, so if you have a bunch of velocities, a bunch of different velocities, like a car whose velocity is changing at time intervals, throughout time, then I'm 100% agreeing with Annie that we are saying as long as the velocity time graph is a straight line, and that could be horizontal or it could be diagonal, like Annie's saying, if the velocity time graph is a straight, and please write this in your notes. I don't want to rabbit hole myself, but please, I mean, anybody, everybody. So yay for Melanie and Annie today, like driving the train in the class. If the velocity time graph is a straight line of any kind of slope, then what we're saying applies. Like then the median velocity is the same as the mean velocity. Yes. And now just to be super explicit about Annie's like good use of language, so where does acceleration come into that? If the slope, well, where it comes into it is acceleration is the slope of the velocity time graph specifically, or average acceleration is the slope of any line connecting any 2 points on a velocity time graph. So what we're really saying is if the velocity can be plotted as a straight line is another way of saying if the slope of the velocity time graph is a constant, right? That's what straight line means, constant slope. So if the velocity time graph is straight, if the acceleration is constant, those are two equivalent statements. That's what we're saying, right? So yes, and sure, that would also mean that if you made if the acceleration is constant, then that means if you made an acceleration graph, I mean, just to fully address every aspect of what Annie's saying, if you made an acceleration graph, which you sure could, necessarily that graph would not only be a straight line, but it'd be definitely a horizontal line. That's like the pro tip bonus extension of what she's saying, right? So what she's saying would still be right. It would be so specifically right, it would be horizontal all the time for the acceleration graph. So that is exactly where I was about. Again, you might think, well, why is Annie bringing him off the topic? No, that's exactly where I was about to go next. So I'm saying then in physics terms, this. So if the acceleration So what we're saying literally is right. And this is where things get subtle. The reason I'm really emphasizing this is hopefully all my words sound like they make sense, like when I say them, but this is a subtle thing. What we're talking about now for the first time in physics is we're talking about constant change. Constant change. Back up for a minute and think about that consciously. That sounds like a contradiction. I mean, maybe it sounds like it's making sense when I'm saying it, but if you really think about it, it's like almost a contradiction, which is why it seeps into the unconscious brain and starts confusing people later for reasons that they don't know why they were confused. We're talking about now something that changes, but in an unchanging way. Like what? Like you need math to even follow that idea. Like we're saying exactly like you could think about it graphs, like Andy's saying, or think about it in terms of numbers, like on the original problem, or think about motion of a car. What we're talking about now, like what we're really saying secretly is we want to focus our attention in physics heavily from now on this weird case of a velocity changing, but not in a changing way, which assumes already that if once you get the idea of velocity and acceleration, you could imagine that when velocity is changing, i.e., when there's acceleration, that could be changing too. And you could imagine that could be changing too. And you can imagine, like, that's the whole idea of derivatives. They go on forever, they're all possible. But we're saying in physics, we're going to stop and focus on the second derivative level. The third derivative is possible, it's conceivable, blah, 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 it's important. But we're saying in physics, there's something very special about the case where a car is getting faster and faster and faster, like 10 miles an hour, then 20 miles an hour, then 30 miles an hour, but doing it in a steady way. Like every minute, it's gaining exactly 10 miles per hour, not more, not less. Like that's constant change. Sounds like a contradiction, but it ain't. It's saying there is a first derivative and there is a second derivative, but there ain't no third derivative. The third derivative is zero. That's what we're saying. We're saying somehow that's a very important case in physics. When A is a constant, when the change exists, but the change in the change does not exist, or well, I should say, really, the change in the change exists, but not the change in the change in the change, right? There's a change in position every moment called velocity. There's a change in velocity every moment called acceleration, but the acceleration staying steady at like 10 miles per hour per second or whatever. That's what we're talking about. And we're saying that when that happens, yes, in English, the mean equals the median. But how can I say that mathematically or in a way that's equationally relevant to physics? I'm going to say this. Hello, where's my colors? Okay, I'm going to say this. Now you're going to want to take notes on this. I don't want to like muddy up the whole sheet, but look, like, what the heck did I just write down? Like, what does it have to do with everything I'm saying? This is a big, important equation, and it's super subtle, and particularly in light of everything Melanie and I were previously talking about. This is subtle and important because notice this now is a double equal sign. It's a double equal sign. I'm not saying that GDPs are never double equal signs. This one is a double. It's a double because it's only true under certain conditions. It's not a definition, but it is fundamental. There's no more fundamental or basic or simple way to write this than this. Like, for example, it could be rearranged to solve for V, like lowercase v, or for V naught, but this is its original arrangement to go into, like, this goes into your list. Like, call this now. And, you know, if we had E, yeah, we had equations through E before, then this would become F. The reason anyway, so this would become F. This is a GDP. But even if you followed everything I just said in English, you still might be like, well, how did that lead to that equation? What does that have to do with anything? And of course, I'm going to tell you, and the video has told you, but I also, even before I tell you, I also really want to alert you. This one is subtle. The reason we had the whole other discussion is to prepare for this one because, first of all, notice you already have you already have an equation for V bar. You already have one, and it's V bar triple equal sign, x minus x naught over t. So if anybody's just instilled the old mentality of just like memorizing a list of equations and just like picking the one out that seems relevant, which was appropriate at one level of physics, it's going to get us into trouble now Because if you're ever having an equation where you sort of know that you're looking for average velocity or something, it's going to be confusing if you just memorize and don't understand them. It seems like we have two equations for average velocity. So how do you know which one to use when? Or do they contradict each other or what? That's number one. Now, first thing I'm saying is when in doubt, use the other one first, because the other one's always true. This one's only sort of true. But second of all, so that's you might want to write that as notes. Like when in doubt, always write the other one first, because that one's never wrong. Second of all, when in doubt, when you're looking for a GDP and you don't know, or you're really stuck in a problem, you like don't know, um, like what to do next, or there's it feels like you don't have enough information in a problem. I'll be even more specific. If you're ever doing a problem and you feel like you have information about, you have like interval information, like you know distance, you know time, but you're supposed to be getting a velocity somewhere at some point, or you know that you need one, or you need a couple because you're trying to get an acceleration, and acceleration needs instantaneous velocity. But anytime you feel like you need an instantaneous velocity, but you don't have it, and it's not even the ultimate goal, it's just something that you're like annoyed because you don't have and you don't know what to do. When in doubt, consider this equation. This equation, and again, if you're just looking for things that solve stuff you're not gonna, people forget this one all the time because it doesn't look like it's solving for anything new, but it's a new way of looking at something. And whenever this one's necessary, nothing else will do. So what is this saying? This one, it's saying, well, it's saying in math what we just said in English. It's saying that as long as acceleration is a constant, then the average of the whole thing is the middle of the whole thing. Like the average velocity, v bar, is equal to the instantaneous exact precise velocity right in the middle, the middle of the what? The middle of the time, because time is always our independent variable. The average velocity for the whole thing is equal to the middle. And again, remember, this is assuming that there's acceleration. So the velocities are changing all the time. You have all these different velocity values, all these different instantaneous velocities. This one's saying if you want to know one of them, if like you feel like you don't know any of them, we can tell you the middle one. You can get the middle one by realizing it's going to be the same as the average from the whole. And what do I mean by the middle one? The first one and the last one added together and divided by 2. What this is saying is if you take the lowest and add to the highest and divide by 2, if you just average the two endpoints of the velocity, you will get the one right in the middle because acceleration is a constant, because the velocities are changing always by a steady interval. So in other words, if you don't even have to, in other words, it's a trick. Instead of adding up all of the velocities, which you don't know anyway if it's physics, instead of adding them all up, you can just add the highest and the lowest and divide by 2, because any information that you lost in the second half of the motion is directly compensated for by any information that you lost in the lower half. Because you gain as much above the middle as you lose before the middle. I'm not saying that well, but you gain, like, that's the best way I could say it. You gain as much above the middle as you hadn't yet gained before the middle. This is a way. All this assumes you got to be really careful about the difference between a letter with a bar over it versus a letter not with a bar over it. Instant. Yeah, that's illegible, but
Can
okay.
you move your screen up? Is it possible to move it, scroll it up so I can see what you wrote at the
Oh
bottom?
yeah, sorry. It's actually okay. It's actually, I don't know if I can scroll, but I'll just write that more neatly. Hold on a second. Yeah, fair, very good question. Hold on a second. So it says a way of transitioning between average V and instantaneous V. I'm saying this is an equation to think of whenever you feel like you need an instantaneous V, but all you have is information like displacement and time for an average, or the reverse, like if you have information about instantaneous Vs, but you ultimately need an average, this is a way of getting you from one to the other. And again, and I remember and this one looks so much like some other equations. This one looks like A bar equals V minus V naught over T. And when I used to try to memorize equations, like everybody else, I tried to memorize equations too. And when I tried to memorize things, I would always get this one confused with the A bar equals V minus the white one that Melanie and I were talking about before. It's like it looks so similar, except and I would try to remember, okay, that one has a T in the bottom, this one has a two, that one is subtract, this one's add, but like, and you can do that. But what I'm here to tell you is like, actually, this totally makes sense. The reason it's V bar, I mean, V naught plus V over two is it's just saying add them up and divide by two. It's an average. Add them up and divide by two. It's the thing that everybody was doing in problems where they weren't allowed. Like it's what people were automatically doing in like the Grandma Grimm problem and the Hill figure problem. They were just taking two velocities and averaging them together. That is, and I said, that's not okay. That's not okay. It wasn't okay in those cases. I'm saying there's special cases where it's okay. We have from here on in. Anyway, so that's what it says. So last thing again on this equation, 9 times out of 10, when you're going to use this equation, you'd have to remember that it exists to think of it. Like I don't know how better to say that. Like it's a light bulb going off kind of moment when you realize, oh, maybe I'll try this equation. Um, so hopefully, okay, so that, chat, oh, nothing in the chat. Okay. And obviously we practice, then that's the point of that homework midpoint velocity. And I'd like, obviously to get back to practice with you all. And that's all we'll do. Well, we should also warn you, that's what we'll get back to you Monday on purpose, because when we're practicing these things, I really like to have the Q&A, like Melanie, Annie, and everybody else. So just to warn you too, even though I will go over these problems, there's like now you have a bunch of problems we haven't gone over yet. I will, but it'll be Monday, not Wednesday, just so you know. Wednesday, the video you'll watch is also totally relevant to all this. It's the next Galileo's principle of relativity. But since it's like its own thing and it's not practicing in Q&A back and forth, like it's better for a video that if that makes sense. So we will practice this more on Monday. You'll have to suspend your hope. And plus Wednesday's when the big old duck is due anyway. So then Wednesday, the video watch is its own thing. Anyway, okay. So what I'm going to do now, I know we have like 17 minutes. I want to quickly show you the other two equations where they come from this. I say quickly. I mean, I'm never quick when I say it, but um, okay. So we're going to derive two other equations right now from this. So again, everything I'm saying from here on in, like indefinitely assumes the special case of constant acceleration of a second derivative that exists as a number. This is, again, sidebar, this is the point of lab 3. Maybe could someone just put in the chat exactly where you're up to in lab? Like what's the next, tell me in the chat privately, someone, like what the very next lab assignment that's due, so I could try to gear my thoughts to help you with that. Like where are you in lab? Oh, great. Thank you. Got it. Formal lab report 2. Okay, so formal lab report number 2. Oh, I said lab 3. Wait, I'm getting confused. So that's the string bolt. So the lab 2 is the string bolt lab, not lab. So when is lab? Oh, I see what's going on. Yeah. Right, lab. Okay, great. Okay, so the whole purpose of lab 2, yeah, right, lab 3 is vectors. Perfect. Yeah. I almost forgot about that. So just so everything that you were lab 2 is like hard, it's like fun and easy in a way to do, but it's like hard to understand in a way for sure. The whole punchline, and I'll try to direct my thoughts more directly if your formal report is due. Like the whole purpose of lab 2 is to get you to see the idea of change that is occurring at a constant rate, and specifically to see that yes, a classic example of a constant change is what happens when an object falls freely to the surface of the earth. Like that, okay. And I understand, like everybody, in the big takeaway of lab 3, it seems really confusing for a while. And anybody who's ever seen any physics in high school or anything kind of thinks that the whole punchline of lab 3 is going to be that magic number 9.8 meters per second squared or whatever. And yes, ultimately we care about that number a lot, but I'm here to emphasize, and lab 3 is here to emphasize, that the issue is not the number. Don't memorize the number. You'll just naturally remember the number after a while. It's not the number that's the issue, because after all, that's just that number 9.81 is only that number because we choose to measure in meters and seconds squared. If we just choose to measure in feet, which we have every right to do, then it would be 32 or whatever. There's nothing magical or divine about the number. What's important, and the big takeaway, is that it is a number, that the number doesn't change, that it's a change in velocity that is unchanging, right? So free fall is a huge example of this whole topic that we're in now. And it's such a big topic that we have a couple other equations that become very useful from here on in for any kind of constant acceleration example, including free fall. So one thing that comes up all the time is, can we get a position function of time? Can we get an equation where the input is time, the independent variable is time, and the output, the dependent variable, is position? Like if you name the when, can I name the where? That's totally the job of a physicist. I want to be able to say where in space something is at a given time. Let's assume now that we know about the concepts of velocity and acceleration. If someone specifies the initial velocity, of course, the velocities are going to change. So if they specify the initial velocity and the initial position, both of these things are going to change. And they specify the acceleration rate, which itself is not going to change, right? You see why I'm writing them differently? Like if they specify those 3 constants, can we come up with a rule or a mapping or an equation to link the input of time to the output of position? And the answer is yes. We can just do algebra on the stuff we already have. So I did it in the video. I'm just going to quietly do it right here so you can copy it down again. But whatever. So we could say. So what I'm about to derive is what you use whenever all the knowns are what I just listed, and you're looking for position, or you want to rearrange it as such. So. What we know. So I'm doing the melody thing. Like what I know are those 2 things, right? So I'm gonna, and I know this. Like these are my, oops, sorry. These are now my GP. I'm allowed to use these as GDPs. So I'm gonna put them. So that would be like my step 3. I can go back. Well, I'll pause for a second so you got. But all those equations we've already stopped. Yeah, right. We know those. So I'm gonna smosh them together algebraically now. Basically, I'm And I'm going to do sort of, again, you can slow this down later or it's in the other video, but remember, what am I looking for? I'm looking for an equation that gets x minus x naught by itself on one side and makes it based on t. So, okay, I'll write them one more time just so you can see. So we have this, we have this, and we have this. So I rearrange. I plug in. And writing this difficult just so you can see. This is an example of what I was saying before. And this is all constant acceleration. Therefore, A equals A naught, which equals A bar. Like they're all the same in this case. If this is so I can get rid of the bars when I want. I'm not going to so so basically I'm saying in English so far, I'm looking at the time, I'm saying displacement equals average velocity times time. Displacement equals average velocity times time. But now for average velocity, I've expanded it out to V plus V over 2. And time, now I have a new, again, see T equals V minus V naught over A. I'm not saying you should memorize that. Don't memorize that. But just know it follows, like another way to put it, if you memorize anything, memorize the GDPs because they give you everything else, is kind of what I'm saying. But so the T equals V minus V naught over A, I can now plug in for T. So I can say, so I have these, I'm just repeating a little bit so you can see. I just do. What did I just do? So, oh my God, I'm doing I'm doing the other equation. Okay. Wait a minute. Sorry. I mean, this is all true, but I just accidentally was deriving the other equation. Sorry. Wait, I'm looking at the time. Is this going to confuse me? Okay, I'm just going to keep, okay. Because this could happen to you on your homework. So look, accidentally, I just got rid of the T. I plugged in for T, so of course the T's went away. I was trying to get an equation for T. In terms of sequencing, I did make a mistake, but I'm not going to erase it or anything because this could happen to you in homework. I want to show you what to do. So look, all this, what I do have here is a truth because I started with a truth and I moved through truth. What I have here, if you FOIL out, this is one of the two equations I just wanted to derive for you. It happens to be the other one, not the first. But look, we're going to call this is equation G. Let me be very clear within 5 minutes. I will still get the other equation for you. This one that I just accidentally did, this one, what was my accident? My accident was I made a substitution for t. By substituting t, the t disappeared, which is not what I originally wanted, but it's useful. What I just got, I got an equation that doesn't have time anywhere in it. So now it's not new information. I just took all the old information and put it together algebraically. But this equation is what you use from now on. Anytime you have a problem where you aren't given any information about the time and you're not solving for any information of the time, right? Like sometimes you might think, wait, I don't need the time. I need the time to do and then you might do a whole bunch of other steps. If you don't have the time and you're not looking for the time, this you can use from now on. Okay, but that's equation G. What I was looking for was equation F. So let me backtrack now. But that is what, okay, and backtrack to F. What I was looking for in F is literally, I wanted an equation that was a function of time. So I'm going to start again with, I've got v equals x minus x naught over t. Therefore, x minus x naught equals vt, just like I did before. And v equals v plus v naught over 2. But now I'm going to do exactly the Melanie thing here. I'm going to say, basically, I'm going to plug in. I'm going to say x minus x naught equals just like this. But since I don't want to get rid of the t this time, that was my mistake a second. I don't want to get rid of the t. What I want to get rid of is that v. I don't know what that v is. Why? Because what's given, I'm assuming a situation where I'm given v naught and x naught and a, but the final velocity I don't know. So what do? I do the Melanie thing. Like I say, okay, well, I don't know v, but I know the a bar. Whoa, hello. A bar, which equals a bar equals v minus v naught over t. So I rearrange this to say v equals a t. Like it's useful here to rearrange and I'm going to plug that in for v. So I know I'm going fast. We've got 2 minutes. I'll scroll back in a second if anybody needs to write after class or anything. But therefore, if x minus x naught equals v plus v over 2 times t, then I'm now saying it equals v naught plus at plus v naught all over 2 times t. And I can collect the like terms and say this is equation F. And this is super important, the position function of time. This is how an object travels in time if it is accelerating at a constant rate. And from here on in, yes, you could, once you set it up, you could plug and chug in it and stuff and all that. But the conceptual, and we have 1 minute and I'm done. The conceptual takeaway of this, as the videos try to emphasize, is that when you're going at constant velocity, your position is a linear function of time. It's directly proportional. If you're going 60 miles an hour, that means every hour you go 60 miles. So if you go 2 hours, you go 2 times 60, 120 miles. They're directly proportional. But if you're accelerating at a constant rate, your position is no longer directly proportional to time. If you double the time, you don't go double the distance. It's directly proportional to the square of time, meters per second squared. Second power, second derivative. So if you double the amount of time that you're going under constant acceleration, you would quadruple the distance that you would have traveled. That's the takeaway. That's class. I will see you. I'm going to hang out for a second if there's any questions or you want me to flip back the notes, but you've been very, very patient and participatory. So I will You'll see me on video on Wednesday, and I'll see you in live on Monday. Pork bless America.